Welcome to This Explainer. I'm absolutely thrilled to be with you today because we're breaking down the foundational building blocks of chemical solutions. Whether you're thinking about how pH balance is absolutely crucial in biology or how salt synthesis drives huge industrial manufacturing, understanding how these substances interact is literally like unlocking the secret language of the physical world. So let's jump right in and decode this chemistry together. Here's the roadmap for our explainer today. We'll be looking at acids, alkalis, and ions, strong versus weak acids, measuring with pH, chemical state symbols, and finally, making soluble salts. Section 1. Acids, alkalis, and ions. Okay, let's get into the fundamental contrast between our two main types of chemical solutions. First, we have acids, which are defined by having a pH below 7. But more importantly, on a chemical level, acids produce hydrogen ions, which we write as H+, when they're dissolved in water. On the flip side, we have alkalis. These have a pH above 7. And instead of hydrogen, alkalis produce hydroxide ions, written as OH- in water. That one simple difference in the ions they produce is the engine driving everything we're going to talk about today.
To ground this in reality, let's look at some everyday examples you'll definitely encounter. For our common acids, we've got hydrochloric acid, sulfuric acid, and nitric acid. Over on the alkali side, we see sodium hydroxide, potassium hydroxide, and calcium hydroxide. Notice a pattern there? Those hydroxide names are a massive, neon-flashing clue about the hydroxide ions we just learned they produce.
Moving right along to Section 2, strong versus weak acids. So why are some of these substances highly reactive and dangerous, while others are actually pretty mild? Well, it all comes down to ionization. A strong acid, like hydrochloric or nitric acid, fully ionizes in water. This means all the acid particles completely split into ions. Because they produce ions so incredibly fast, they have a lower pH and are much more reactive. A weak acid, like ethanoic acid, only partially ionizes. Only some of its particles split up. Consequently, weak acids have a higher pH than strong acids, and they're way less reactive. It's really just a matter of how completely they break apart in the water.
Section 3. Measuring with pH.
The pH scale is honestly brilliant in its simplicity. It measures exactly how acidic or alkaline a solution is, strictly on a scale from 0 up to 14. The rules are super straightforward. From 0 to 6, you've got an acidic solution. The lower that number drops, the more acidic the solution is. But from 8 up to 14, the solution is alkaline. And naturally, the higher that number climbs, the more alkaline it gets.
Now, you might be wondering about the number exactly in the middle, 7. A pH of exactly 7 represents a perfectly neutral substance. It's neither acidic nor alkaline. It sits right at the perfect balance point of the scale. But how do we actually figure out a pH number in the lab? We use something called a universal indicator. It changes color depending on the pH of the solution, and these colors tell a really vivid story. Red indicates a strong acid. Orange or yellow signals a weak acid. A perfectly neutral substance is going to turn green, and an alkali will turn the indicator blue or purple. You just take that color, compare it against a standard pH chart, and you've got your exact pH number. It literally takes an invisible chemical property and paints a picture for us. Section 4. Chemical state symbols. Whenever we write out chemical reactions, we need to know exactly what physical form our interacting substances are taking. We use 4 vital state symbols, usually written in little brackets right after a chemical formula. A lowercase s stands for solid, an L is for liquid, a G means it's a gas, and AQ stands for aqueous, which is just a fancy way of saying the substance is dissolved in water. Let's see how these symbols work in practice. If we have hydrochloric acid reacting with sodium hydroxide, we'd see an AQ after both of them. They are both dissolved in water. They react to form sodium chloride, which is also aqueous, and water, which gets the L state symbol because, well, it's a liquid. Reading the equation this way gives us a complete, perfect picture of the chemical environment we're dealing with. This brings us to a pivotal question, and really the main event of our explainer. We know what acids are, we know how to measure their strength, we know how to read their state symbols, but what actually happens when an acid reacts with a metal, a base, an alkali, or a carbonate? Let's find out in Section 5, making soluble salts.
The crucial takeaway here is this definition. A salt is simply the substance made when an acid reacts with a metal, base, alkali, or carbonate. That is the ultimate goal of these specific chemical reactions. When you put an acid together with one of those 4 specific ingredients, boom, a salt is born.
What's really amazing is that you can predict exactly what family of salt a reaction will produce just by looking at the acid you're using. It follows a rock-solid general rule. If you use hydrochloric acid, you're going to make chlorides. If you use sulfuric acid, you'll make sulfates. And if you use nitric acid, your reaction will make nitrates. It is incredibly orderly. Let's look at a concrete example to see this naming convention play out in real time. Say we take sulfuric acid and react it with copper oxide. Following a rule, sulfuric acid always produces sulfates. Therefore, the resulting salt is copper sulfate plus water. The name of the salt literally tells you exactly what its parent ingredients were. If you actually wanted to perform this reaction to produce a soluble salt in a lab, you'd follow a very structured method. It's kind of like a recipe. Step 1, warm the acid gently. Step 2, add an excess of your insoluble base. Step 3, stir it until the reaction completely stops. Step 4, filter the mixture to remove any of that excess solid base left over. Step 5, heat the remaining solution so the water begins to evaporate. And finally, step 6, leave the solution to crystallize and dry the resulting crystals. This elegant process transforms liquid acidic solutions and base solids into perfectly formed, dry salt crystals. We've covered a tremendous amount of ground today, from the basic ions that make solutions acidic or alkaline, all the way to the precise steps of salt synthesis. So I want to leave you with this thought. Knowing the reliable rules of acids producing specific salts, understanding exactly how pH dictates reactivity, and having the ability to decode state symbols, what unique chemical salt combinations could you synthesize next? The toolkit is now yours. Thank you so much for joining me for this explainer, and keep exploring the fascinating world of chemistry.